इक्विवेलेंसेस हमने किया है कंप्लीट, है ना, उसके जो रिलेटेड रिजल्ट्स है वो भी हमने कुछ किए. सो टुडे आवर टॉपिक इज कॉन्ग्रुएंसेस. Congruences. Let S be a semigroup. Let S be a semigroup. Let S be a semigroup. A relation R on S. A relation R on S is called left compatible. Is called left compatible. Is called left compatible if for all if for all S T A in S, ST belongs to R implies. Left compatible means we multiply on left side, okay, by A. AS, AT, this should also be in R. And right compatible, and right compatible if for all ST A in S, one has the following: ST belongs to R implies SA TA belongs to R. Okay, this relation is called compatible. It's called compatible. It is called compatible. It's called compatible if for all ST S dash S prime T prime belongs to S, one has the following: ST belongs to R and S dash T dash belongs to R. This should imply the product S dash T dash belongs to R. So this is the definition of left compatible, right compatible, and compatible relation. Okay, now we define left congruence and right congruence. A left right compatible, जो लेफ्ट राइट कंपैटिबल हो, लेफ्ट कंपैटिबल राइट कंपैटिबल, इक्विवेलेंस और इक्विवेलेंस भी हो, is called a left right congruence. Is called a left right congruence. Is called a left right congruence. And a compatible equivalence relation is called a congruence. अगर compatible होगी, a compatible a compatible equivalence, जो compatible भी हो और equivalence भी हो, compatible equivalence relation is called a congruence, is called a congruence, is called a congruence. So example, you can take set of natural numbers with usual multiplication and with usual order. The set of natural numbers, the set of or positive integers, the set of natural numbers is a semigroup, is a semigroup with respect to the multiplication, with respect to usual multiplication, with respect to usual multiplication, and the relation less or equal to is a congruence, is a congruence on n. This relation is a congruence on n, because if we have n1 less or equal to m1, n2 less or equal to m2, then n1 n2 is less or equal to m1 n2. So it's a compatible relation, and this relation is, but it's not equivalence. Okay, sorry, this relation is not equivalence. This relation is not less or equal to, is not equal, it's a partial ordering. So how do we define the relation congruence on this n? So congruence relation on n. If we define if and only if the difference is an even integer, like that, so let's define this relation. Define a relation on n, the set of natural numbers, by define relation R on n by, we say this n m belongs to R if and only if n minus m is an even integer, is an even integer. So this relation is an equivalence relation. So is it compatible? It's clearly compatible, because whenever we have n1 m1, they are all relative, n2 m2, they are all relative. It means that n1 minus m1 is an even integer, n2 minus m2 is an even integer. So which gives that so if it is an even integer, it means that either both are odd or both are even. So you can easily verify that. Verify whether the above relation is congruence or not. Whether the above relation is congruence or not. Is congruence or not. Okay, so let's now prove the following theorem. It is a proposition. A relation rho on a semigroup S. A relation rho on a semigroup S. On a semigroup S, a relation rho on a semigroup S is a congruence, is a congruence if and only if it is both left and right congruence. If and only if it is both left and right congruence. If and only if it's both left as well as right congruence. Proof. So let rho be a congruence on S. We show that it's both left as well as right congruence. Let rho be a congruence on S. Now we prove it's both left as well as right congruence. So for this we take three elements. Let S T A belongs to S such that this S T, they are row related. We show that AS and AT are also row related since A is row related to A because rho is an equivalence. It's a congruence relation, so it's first an equivalence relation. So that means A is related to A, row related to A. So now we apply the compatibility. Since the relation is compatibility, if we have two pairs which are row related, then the product is also row related by compatibility. So this gives AS, AT belongs to row, this product as well as this product. As a TA belongs to row, and hence row is a left as well as right congruence. Hence row is a left as well as a right congruence. It's also a right congruence. Now conversely, we assume that rho is both left and right congruence. We'll show that it is a congruence. It's a congruence. Conversely, assume that rho is both left and a right congruence. Right congruence. We show that rho is a congruence. That means we need to show that rho is actually compatible, because congruence means compatible and equivalence. So rho is given equivalence because it's left as well as right congruence. So by left congruence we mean left compatible and equivalence. Okay, so it's an equivalence relation. We need to show that it's a compatible relation. So now let's choose 4 points. Okay, for the compatibility, let S dash T dash belongs to S such that S is row related to T and S dash is row related to T dash. Row related to T dash. We show that this SS dash T dash they are row related. They are row related. So this gives this gives, since ST is row related, so it means that S dash T S dash also belongs to row because row is left right compatible. Row is right compatible because row is right compatible. Also we have s dash t dash, so also by left compatibility, since s dash t dash they are row related, multiplying by s here we get this s dash s t dash, they belong to row because row is left compatible. Row is left compatible. Row is left compatible. Okay. Because your row is left compatible. So since now this row is transitive, we have ss dash ts dash, and actually we need to show that ss dash, so it's ts dash and st dash. Okay, we need to apply the transitivity. We have ss dash ts dash and ts. Okay, let's okay, here we should write here this because we need to apply the transitive property of row, so we should write here this is here ts dash, so here we should write t, okay, instead of s. ts dash tt dash, again it is by left compatibility. Actually instead of s we write here t. Now we apply the transitive property of row. We have ss dash ts dash, they are row related, and ts dash tt dash, they are also row related. So therefore ss dash tt dash belongs to row because row is transitive. Row is transitive. So thus this proves the theorem. Hence this row is congruence. Hence row is a congruence. Row is a congruence. So next we define a quotient semigroup. Okay. So quotient semigroup actually. So let row be a congruence on S. We define multiplication on S over row, which is the set of classes x belongs to S. We define multiplying on this by we choose two elements, say x row, y row. The product is equal to xy, row class of xy. So first we see this multiplication is well defined. The above multiplication is well defined. The above multiplication is well defined. So for this we take two equal elements of S cross S, not S cross S, S over row cross S over row, because it is the operation on S over row. So let's choose two elements. Let's choose say x row y row and s row t row. Let x row y row and s row t row belongs to S over rho cross S over rho such that they are equal. X rho y rho is equal to S rho T rho. Okay. So we need to show that the product x rho y rho should be equal to S rho T rho. So their product should be same. So that's what do we mean by the well-defined index of multiplication. So they are equal. These two pairs are equal. Okay, these two pairs are equal. We must show that x rho y rho is equal to S rho T rho. So this gives this equality gives x rho is equal to S rho and y rho is equal to T rho. Okay. Row class of x and row class of s it's same, and row class of y, row class of t, they are same. So first equality gives x is row related to s, and the second equality gives this y is row related to t. Okay. So this gives this x s belongs to row and y t belongs to row, and which implies that since row is a congruence, it means x y s t they are in row. So that means the row class of xy is equal to row class of st. So that means the product is unique. So or we can say this x row y row is equal to s row t row. So this is a binary operation on S over row. Next we check this multiplication is associative. The above multiplication is associative. Multiplication is associative. So for this we choose three elements in S over row. Let's choose three elements. Let's choose x row, y row, z row belongs to S over row. Then let's find this product x row and then y row, z row. This is equal to x row and this thing is equal to yz row, and that is again equal to x yz row. But now we can apply the associative property of the elements on x y z. It's equal to x y z row, and you can see this thing, it's equal to x row, y row, then z row. So this proves the associativity of the operation. So hence S over row is a semigroup. S over row is a semigroup, and it's and we call it the quotient semigroup or semigroup factored by row. Okay. Therefore, Therefore S over rho is a semigroup, is a semigroup. Next we have a theorem. Let S be a semigroup and let rho be a concurrence on S. Let S be a semigroup and rho be so let's name this theorem 1. Okay, here it is theorem number 1, and rho be a congruence on S. Then this map rho natural from S over rho, from S over rho to from S to S over rho, sorry, from S to S over rho is a morphism, is a then this map defined by the image of X under this rho natural is equal to the rho class of X. This is a morphism, is a morphism. तो प्रूफ इसका आप खुद देख लोगे. Proof is an exercise. And this morphism is called the natural morphism from S to S over rho. It's called a natural morphism. In fact, this morphism is also onto, so if we choose any element in S over rho, we must choose some X in S such that this the image of that X under rho natural is equal to X rho. It's onto, it's trivial. This map is onto. So the next theorem, theorem number 2. Theorem number 2. Theorem number 2. Let T be a semigroup. Let S and T be semigroups. Let S and T be semigroups. And we have a map phi from S to T. This be a morphism. Be a morphism. This map be a morphism. Then the relation which we called the kernel of map. This it's the relation which is actually phi composition, phi inverse, and we have seen that this is this consisting of those elements A B in X S cross S. It's a relation on S such that A, image of A under phi is same as image of B under phi. This relation, so here's a map, then the relation this is a congruence. ये हमने चेक किया था, ये रिलेशन इक्विवेलेंस से. अब हम प्रूव करेंगे ये रिलेशन कॉन्ग्रुएंस से अगर ये मैप S पर हो और ये सेमी ग्रुप्स के दरमियान होगी. इज ए कॉन्ग्रुएंस, इज जैसे ग्रुप्स में है ना, ग्रुप्स में क्या होता है, ग्रुप्स में अगर आपके पास दो ग्रुप्स होंगे और फाई होगी इनके दरमियान मॉर्फिज्म, देन कर्नल ऑफ फाई क्या होता है, नॉर्मल सब ग्रुप है ना. तो उससे आप क्वेश्चन डिफाइन कर सकते हो। तो यहाँ पर क्या है, यहाँ पर एक्चुअली नॉर्मल सब ग्रुप्स तो नहीं होगी, यहाँ पर कॉन्ग्रेंसेस होगी, क्योंकि यहाँ पर कॉन्ग्रेंसेस से एक्चुअली आपके पास क्वोशिएंट सेमी ग्रुप्स आते हैं। सो हियर द कर्नल ऑफ फाइव इज एक्चुअली कॉन्ग्रेंस, सो वी कैन फैक्टर आवर सेमी ग्रुप एस बाय कर्नल ऑफ फाइव. It is the same actually. This is a congruence. This is a congruence on S. Okay, it's a relation. It's a subset of S cross X, and there is a monomorphism, and there is a monomorphism. There is a monomorphism. Let's denote that by alpha, which is from S over kernel of phi to T. There is a morphism from this to T such that image of alpha is same as the image of phi. दोनों की इमेज सेट सेम है, and the diagram commutes, and the diagram, so diagram is this thing. It's from S to T you have a morphism phi, then obviously you can define this map, which is a natural map from S to S over kernel of phi, because kernel of phi is a congruence, so this is well defined. S over kernel of phi is a semigroup, and the map is the natural map, which is rho natural. Here rho is kernel of phi, it's kernel of phi natural. This map from S to S over kernel of phi, and we have a morphism from S over kernel of phi to T. This morphism, which is alpha, such that this diagram commutes. commutes का मतलब क्या है? that is, commutes का मतलब ये है, अगर आप इन दो का कंपोजिशन लोगे, kernel of phi natural composition alpha, this composition should be equal to phi, that is kernel of phi natural composition alpha should be equal to phi. So this is the statement of the theorem. So first we need to verify that kernel of phi is a congruence. Proof. We know that kernel of phi is an equivalence. This we have already done. We know that kernel of phi is an equivalence. Now we show that it's also a congruence. Now we show that it is also a congruence. It is also a congruence. So for this we choose two pairs in kernel of phi, and we'll show that their product, their component wise product is also in kernel of phi. So let's choose two pairs. Let in kernel of phi, okay, in kernel of phi means let's choose this a kernel of phi. So we should denote this relation okay, so let's choose okay, there should be some simple notation. So let's use the following notation. Let assume that let's put this relation K is equal to kernel of phi, और वो हम केस का ज़्यादा यूज़ नहीं करते. Let's denote this by rho. Okay, this rho is a congruence. Put this thing. Okay. Okay, by putting this, we prove the following. So let's take these pairs A row. Okay, A B belongs to row. Sorry, A, yeah, or you can say S. So kernel of phi is an equivalence. ST belongs to row, and S dash T dash belongs to row. So they are row related, means that their images under phi are same. So that S phi is equal to T phi, because row is kernel of phi, and S dash phi is equal to T dash phi. So this means what's this? S dash phi. This is equal to S phi T phi, but our S phi is the S dash phi, and this thing is the T dash phi, and that's equal to S dash T dash phi, which implies that S dash comma T. Okay, this is a S dash equal to S phi T phi, or it's a S dash. Okay, S dash. It's actually this actually S